All right, today we're going to look at 9.2 polar equations and graphs. We talked about last time what polar equations look like. Instead of an x and y component on a rectangular grid, the polar graphs, polar coordinates and grids are circular, and they deal with radii and angles from the horizontal. So rectangular points, which are x and y on an xy grid. So it's a combination of trigonometry and geometry. The definition of a polar equation. An equation is polar if its variables are in radian and degree measurements, which are radian. These equations are called polar equations. And the graph of those are, it's not the x and y anymore. This is 0 degrees, pi over 2, pi, 3 pi over 2, and 2 pi. So the radii, are the distances from the center, so on and so forth. So that location is the radius and the theta that created that terminal site. All right, so let's look at identities. As you see on your sheet, I said the first part, identify and graph polar equations by converting them to rectangular equations. Let's example. ID and graph the equation R equals 3. Because this is in radian measures. It says the radius is 3. We have to correlate that into our rectangular coordinate system. When we do this is we know what? We know a squared plus b squared equals c squared. But c is actually the radius. And a is the x component, b is the y component, and c is the radius. So how do we convert this to this equation? Well, we have to get r squared. Multiply both sides by r. Or not yet. We square both sides in this one since it's radius r. If we square both sides, then we have x squared plus y squared equals 9, which is the equation of a circle. That's what we have in rectangular coordinate system. What's the graph going to look like? The center is at 0, 0, and the radius is 3. So center is 0, 0. The radius is 3. And there's our graph. It is because all we had was the radius. The graph of this polar coordinate, which simply have been to be the horizontal since there's no angle. It's on the horizontal axis. Example 2. Identify the equation theta equals pi over 3. What we have to do is we have to relate to what this means. So if theta is pi over 3, it's theta. Only thing we know from there is we can convert the x and y components. So the only thing that we can use to convert this into an x and y component is by using the tangent. Because we have this theta, we have this 90-degree angle here. So we have the opposite and the adjacent. We don't know the radius. So all we have left are the opposite and the adjacent. So if we take the tangent of both sides, tangent of theta, SOHCAHTOA, is opposite over adjacent, which is y over x. The tangent at pi over 3, what's the value of tangent pi over 3? How would you figure that out? Unit circle, exactly. So we have the sine at pi over 3 divided by the cosine at pi over 3. Which is radical 3 over 2 over 1/2, which becomes radical 3. Again, you're going to have for this and the next section, you're going to be using your trig identity charts and your tables. So it'll be much easier to do it that way. So we know that this equals radical 3. Converting this to rectangular coordinates, multiply both sides by x. We have y equals x radical 3. There's the rectangular comparison to theta equals pi over 3. What would the graph of that one look like? the slope is radical 3 over 1, and it crosses at the origin. So x is 1, y is radical 3, which is bigger than 1. It's just short of 2. So it would look something like that. Because it wouldn't be 1 to 1, because radical 3 is a square root of 1 is 1. Square root of 4 is 2. Square root of 3 is closer to 2, so about 1.7, 1.8. So for every 1, I go up 1.8. Over 1, 1.8. Well, so it's a little bit higher than 1 to 1. But that's a conversion there. Example 3. Identify and graph the equation r sine theta equals 2. What do we know about this? We can say, okay, if y equals r sine theta equals this, that means y is equal to 2. What does this graph look like? Going through 2.
Oh, yeah.
Yes. So that would be the rectangular component to it. It would simply be the equation y equals 2.
Oh,
R cosine theta equals -3. Same thing. Cosine deals with which axis? The x-axis. So this would be the same thing as x is r cosine theta. So x is equal to -3. So it's a vertical line going through -3. Theorems are pretty important entities. They give us the formulas we need to solve these equations. So this graph goes through -3. It's a vertical line. It goes through -3. The only reason it's a vertical line is because that's cosine. If it was sine, then it'd be a horizontal line go to -3. Look at the theorem that's on your sheets. Let A be a real number. Then the graph of the equation r sine theta equals A is a horizontal line at y equals A. If A is positive, it's above the x-axis. If A is negative, it's below. And conversely, if our cosine theta equals A, then it is a vertical line. Through X equals A. Same conditioning. If A is positive, to the right of the y-axis, it's left, it's negative. This would have been easier for the first three problems if we had the theorem first. Because they gave us the examples first and then they stated the theorem that we just worked with. Example 5. R equals 4 sine theta. It's different than the earlier ones. Because the earlier ones had R sine theta equals 4, or R cosine theta. This one is R equals 4 sine theta. So what we have to do, we're in the process of converting it to rectangular coordinate system. What do we have for R? Do we have anything in the rectangular coordinate system that we deal with? We have R squared. So we could multiply both sides by R. Remember, we're trying to get, what does it mean to rectangular coordinate system? We want everything in terms of X and Y instead of R and theta. So what is R squared? X squared plus Y squared. What about R sine theta? That equals Y. Remember, Y is equal to R sine theta. X is equal to R cosine theta. So now what do we do? We have Y's on both sides. That's not going to help us any. We have to now solve for, remember, these are unit circles. These are circles we're dealing with. What is the origin of our circle? What is the center of our circle? So we have to move it, everything over, make it equal to 0. And we have to use complete the square to solve this one. Remember how to use complete the square? What do you have to add to both sides? You have to add b over 2 squared. I should put it over here. B over 2 squared to both sides. B is the middle term. So it's 4 over 2 squared. I have to do it over here also. So 4 over 2 squared. On the left side, only do what's inside the parentheses. Don't square it because we have to square root it later on anyway. On the right hand side, work it all the way out. So to complete the square process was we have to add b over 2 squared to both sides. Now, once we have that, take whatever's under the squares and the first sign. So y minus 2. So there's our rectangular circle. Where's the center at? Remember, circles were x minus h squared plus y minus k squared equals r squared. That's the equation of a circle, where the center is at hk and r is the radius. Algebra review. So what's the h for this one? 0. There's nothing there. 0. So it's 0. And this one, positive 2. It's always the opposite. If it's inside the parentheses, it's always the opposite. And what's our radius? 2. Very good. That's r squared. Very good. Why do we need to know this? Because we have to graph it also. At the center is 0, 2. And the radius is 2. So from the center, I go up 2, I go down 2, I go left 2, and I go right 2. So there's my circle. There's my graph. So remember, whenever we're going from polar to rectangular, we have to try to get into terms of x and y. Example 6. Identify and graph the polar equation of a circle. So our equation is r equals negative 2 cosine theta. Same thing here. What do we have to do? Do we know anything? Do we know any equation for r? In what's that? Yeah, we have to make it squared because we have r squared. So the only way we make it r squared, we can't just square both sides because then we square this one. So we multiply both sides by r. Why do we multiply by r? Because look at the right hand side. Remember, our x component is x cosine theta, r cosine theta, and y r sine theta. All we have is cosine. We need to have an r there. So we multiply both sides by r. So r squared is x squared plus y squared. R cosine theta is x because of that. Move the x term over, get them all together because it's the equation of a circle. So we add 2x to both sides. So we have x squared plus 2x plus y squared equals 0. Now we got to complete the square. So what do we have to add to both sides? Yeah, so b is 2. So it's 2 over 2 squared 2 over 2 squared. Remember, only do inside the parentheses on the left-hand side, so it's 1 squared. And work it out. So it's 1 squared is 1. Take the first term, the first sign, and the last term. Whatever's under the squares, put them inside there. So it's x plus 1. So the center of our circle is where? Always the opposite of some parentheses. -1, 0. And the radius is 1. So our center is at -1, 0. The radius is up 1, down 1, left 1, right 1. So there's our graph. So that's the hard part, is trying to convert your equation into x and y components. So you're back down to polar coordinates, rectangular coordinates. The next theorem you have on your sheet here. Suppose a is a positive real number. Then r 2a sine is a circle, radius a, center at 0a. Why is it 0a? Because there's no cosine. Cosine is the x component. That's why cosine 0. R equals -2 sine 2a sine theta. Again, the radius is a. The center is at 0, -a. This one's at cosine, so it's a comma 0. Radius is a. A is comma 0, and the radius is a. Can the radius ever be negative? Notice all these radii always, because remember, what do our equations look like? So whatever's in front of the sine and cosine, those are our radii. And if it has a multiple, call them vectors by now, but if it has a constant multiple, don't worry about those. It doesn't affect the radius. All right. Why is checking for symmetry important? It doesn't have to be circles though. We're gonna look at stuff that are called lemniscate or cardioids, which are equations that will have this shape. It looks like heart. They're symmetric. The reason symmetry is important is if we know the equation is symmetric, then that takes care of half of our points we have to find. If it's symmetric about the x-axis, y-axis, or the origin, we don't have to plot all the points. We just have to plot a few points and then just flip them over or up and down. So basically, it's all symmetry does is help us decrease the number of points we have to try. Test polar equations for symmetry. Similar to rectangular coordinate systems. If we have a point on XY, what is this reflective about? Symmetric about which axis? The y-axis. So if we had XY, then we're symmetric about the y-axis. If the y is, then it's symmetric about the x-axis, right? The same thing works for us. We can look at this. Can you take a negative theta? Yeah, because traditionally, if we have a theta, then it goes counterclockwise. That's theta. If I have a negative theta, then it goes clockwise. So yes, for both of those, we can find points of symmetry with respect to x and y. The next theorem, the test for symmetry, you have to do these for each of your equations. The test for symmetry. Symmetry with respect to the polar axis, the vertical axis, or the origin. The x, y, or origin. In a polar equation, replace theta by negative theta. If an equivalent equation results, the graph is symmetric with respect to the polar axis. Remember, polar axis is your x-axis. With respect to the line y equals pi over 2. Line y over pi over 2 is a vertical line. That's the y-axis. If a polar equation theta is replaced by theta minus pi minus theta, an equivalent equation results, then it's symmetric about the vertical axis. Why pi minus theta? Because in a polar equation, replace theta by pi minus theta. If an equivalent equation results, the graph is symmetric with respect to the y-axis, or the vertical line y pi over 2. Right. If you add pi to it, then it's instead of going up, it's going down now. Right. And the last one, in a symmetry with respect to the origin, in a polar equation, replace r with negative r and theta with theta plus pi. If an equivalent equation results, then it's symmetric about the origin. Again, why we do here with plus pi is because we have to keep on going in the same direction. We're going counterclockwise. As it says further in there, these are sufficient conditions, but not necessary. In other words, they don't need to exist for these things to be true. But if they do exist, it makes our life easier. So let's look at number 3. Graph by plotting points. What's upsetting me is that, remember at the beginning of the semester, we lost almost 4 weeks because we didn't have a system up and running. Yeah. I mean, we should have been finished 2 weeks ago, a week ago. But because we lost 4 weeks, it took them that long to find out what was wrong. We're now struggling to finish up. It upsets me. Example 7. Graph the equation r equals 1 minus sine theta. So how would you graph this? The easiest thing to do is plot some points. I mean, we have not all of them. We have a lot of the 30, 45, 60, 90, all those other angles for sine. We can convert those. What's another way we can graph it? What would the graph look like? Well, it is a cardioid, but how? Because we know it's a cardioid because, well, first off, we're doing irradian measures, our polar coordinates. If we just had this, what would the graph look like? What's the sine function look like? At 0, it's 0, pi over 2, 0. So the sine function looks like this, and it keeps on going forever. The negative of it means it's flipped. That's negative. Now we go up 1. So our graph would be like this. But that's rectangular. We're not dealing with rectangular. Because of the r in front, we're dealing with polar coordinates. So that's why it'd be easier if we just use a table right now. So which values would you throw in there? Actually, all of them, positive and negative. We'd start off with 0. Then we'd start off with pi over 6, pi over 4, pi over 3, pi over 2. That brings us to the very top. Then we go the other direction. Negative pi over 6, negative pi over 4, negative pi over 3, and negative pi over 2. So what would 0 give me? 1 minus sine of 0 is 1. Because that's 0. Pi over 6. 1 minus sine of pi over 6. Sine pi over 6 is what? is 30 degrees, but sine of 30 degrees is what? Look at your cheat sheet. That's cosine. One minus 1/2 is 1/2. Pi over 4. So 1 minus sine pi over 4 would be 1 minus square root of 3 over 2, which is 2 minus radical 3 over 2. Square root 2 over 2. I'm sorry, square root 2 over 2. Square root of 3. That's sine of pi over 3, which is 1 minus square root of 3 over 2. Makes it 2 minus square root of 3 over 2. One minus 1 makes it 0. 1 minus sine negative pi over 6. Is sine an odd or even function? Why? They both do. What does it mean, odd or even? Odd or even simply means this. If I take a positive theta and I put a negative theta, the same value in there, will the sines, cosine deals with the x-axis. So cosine, it will have the same value. So cosine is even. Whether it's positive or negative, it'll keep the same answer, same signs. Sine, on the other hand, oh, that's what you meant by instead of, or it's the x-axis that flips around. It's much easier to look at it this way. Positive angles, negative angles. Sine values deal with the y-axis. This is positive, that's negative. So they're opposite signs. Cosine, whether it's here or here, it's still going to be the same value. So sine is odd, cosines are even because they keep the same value. So because sine is odd, and I put -6 in there, it changes this to positive. But it's going to be 1 plus 1/2. It's going to be 1 plus 1/2, makes it 3/2. Then pi, basically, all of these do here, since they're negative angles, it changes the sign in the middle. So it makes it 1 plus square root of 2 over 2, which is 2 plus square root of 2 over 2. 2 plus square root of 3 over 2. And then this one is 1 plus 1 is 2. How would you graph that? Any questions first? Any questions where I got these values from? Remember, the first column is your angle. The second column is your radius. So when you graph these, there's R1, there's R2, there's R3. So when theta is 0, R is 1. When theta is 0, R is 1. At pi over 6, it's 1/2. So pi over 6, that's positive angle. At 30 degrees, it's 1/2. At pi over 4, that's 45 degrees. It's 2 minus 1, it's just under 1/2. Pi over 3 is a little bit smaller. At pi over 2, it's 0. Straight up and down. At negative pi over 6, it's 1 and 1/2. At pi over 4, it's 3.2 over 2. At negative pi over 3, that's 60 degrees. That's 1.7 over 2. And at negative pi over 2, it's ready. So because of symmetry, we have our cardioid. Well, all we have to do is do one side, and because of symmetry, it'll flip over. All right, you see on your sheets the definition of cardioids. Simply, cardioid is Latin for heart. If R equals A 1 plus cosine theta, R equals A 1 minus cosine theta, R equals A 1 plus sine theta, or R equals A 1 minus sine theta. And A has to be positive, the scalar multiple. So that's a cardioid. There's a whole field of mathematics that deals with taking equations to create different types of objects, different types of shapes. There's an author named Cezanne. All of his books, the front of the covers of the book is, after he finishes the book, he spends weeks just looking for the perfect equation to draw the best graph. They're usually something like Mobius strips in different. A Mobius strip is a strip that, if you follow it all the way on, the outside edge will always be the outside edge, even though it rotates about itself. But it's pretty cool. I'll show you pictures next time of them. So example 8. Limation without an inner loop. I'll show you what this. It's like a form of a lemniscape. R equals 3 plus 2 cosine theta. Because the first thing you have to do is see, is it symmetric? If it is symmetric, about which axis? Because again, it'll make life much easier for us if we could just minimize the work we have to do. So check symmetry. The x-axis or the polar axis. To check polar axis, we change from theta to negative theta and seeing if it changes. So cosine is going to stay the same values, sine is going to change values. So theta to negative theta. So we have r equals 3 plus 2 cosine theta. I change it to r equals 3 plus 2 cosine negative theta. Since cosine is an even function, they stay the same. So this one remains the same. So symmetric about the polar axis, which is the x-axis. Since a lot of us still think in rectangular coordinates, now let's look at the y-axis, or the line theta equals pi over 2. You do this, change theta to pi minus theta, and see if it stays the same. So r equals 3 plus 2 cosine theta. I change it to r equals 3 plus 2 cosine pi minus theta. Look at your formula sheets. You have cosine A minus B, the difference rules for cosines. Well, cosine is cosine cosine plus sine sine. So it's cosine pi cosine theta plus sine pi sine theta. Cosine of pi is what? Negative 1. And cosine theta, so it's negative cosine theta plus sine pi 0. So the sines are 0. So this thing becomes 3 minus 2 cosine theta. Since they're not the same, not symmetric about the line theta equals pi over 2. So it's not symmetric about the y-axis. They just kicked on the air conditioner, didn't they? The air conditioner just now kicked on. There's cold breeze blowing through. So that's the first two. The third one that we're supposed to test is a symmetric about the pole. Remember what the pole was? The pole is where you begin. And in our case, we always start at the origin. So basically this one is across the origin. So the third one is origin or about the pole. So when you test symmetry about the origin, you test two things. You test X and Y, and then X, positive X, negative X, and then Y, positive Y, negative Y. You have to do them both. But what happens here, our equation 3 plus 2 cosine theta, if we change Y to R to negative R, is that true? No, because it puts it on the other side, other quadrant across the origin. So it is not symmetric about the pole or the origin. Okay, so first we test symmetry. So we know this, our graph is symmetric about the x-axis or the polar axis. It's not. So what's the next thing we check according to our theorem? So we looked at this, the pole symmetry. Is it symmetrical with the x-axis, the y-axis, and the origin? We found out it's only this one. So here, now all we do is plot some points. Now, plot some points. So we have theta as our input, our x input. R is equal to 3 plus 2 cosine theta. So we'll start at 0. We'll go pi over 6, pi over 4, pi over 3, pi over 2. Oops. 2, 3. No, so it's pi over 6, 3 pi over 6. 4 pi over 6, 3 pi over 4, 2 pi over 3. So what are we getting there? If cosine is 0, 3 plus 2 cosine of 0 is 3 plus 2, makes it 5. Three plus 2 cosine pi over 6. That makes it 3 plus 2 radical 3 over 2, which is 3 plus radical 3. 3 plus 2 cosine square root of 2 or pi over 4, which makes it 3 plus 2 square root of 2 over 2, makes it 3 plus square root of 2. And it's just 3 plus 2 times 1/2. So it's 4. 2 cosine pi over 2. Pi over 2 is 0, so it's just 3. Pi over 6 is 2 pi over 3. 3 plus 2 cosine 2 pi over 3 makes 3 plus 2 negative 1/2. That makes it 2. Negative square root or negative 3 pi over 4 makes it 3 plus 2 negative square root of 2 over 2. 3 minus square root of 2. Pi over 6. 2 cosine 5 pi over 6. 3 plus 2 negative radical 3 over 2. 3 minus radical 3. Three minus 2 is 1. Now we got to plot each of these. This is the length from the distance from the origin. This is the angle they're going. At 0, 1, 2, 3, 4. It's 5. At pi over 6, which is 30 degrees. We have 3 plus 1.7, so 4.7 at 30 degrees. There's 30 degrees. At 45 degrees, 3.1 something. Sixty degrees, it's 4. Just there. Okay, so looks at this so far. Beta's pi over 2, it's 3. Gonna be symmetric down here. Oop, that's 3 there. 4 there. Two, 2. Times 4 is 500 equals 2 there. 3 minus, that's 2 point something. Something like that. You see, you have to have a, my circles aren't, my radii aren't that clean, so my graphs look horrible. But you just, each of these angles, I go to each of these angles, that's how far I go from from the center. Each of these are that far from the center. And I plot the point. Yeah, so clearly it is, you need to have graph paper or a computer to do it. Or a compass and a protractor. Okay, definition of Le Macron. What they're talking about without an inner loop, what these equations look like sometimes are like this. You can have that kind of stuff, but these are doing without inner loops. So without inner loops, it's characterized as R equals A plus B cosine theta. R equals A minus B cosine theta. R equals A plus B sine theta. R equals A minus B sine theta. The difference between these graphs, like we just did one that was A plus B cosine theta. Ours looks like this. If it was A minus B cosine theta, it would be the other direction. If it was sine, it would go up and down. This is, and then likewise this. So if it's vertical, it will grow up and down. If it's sine, if it's horizontal, it's a cosine function. Example 9, R equals 1 plus 2 cosine theta. Remember, first thing we have to do is check symmetry. Is it symmetric about the pole? Is it symmetric about the polar axis, the line pi equals pi over 2, and the origin? The polar axis, which is the x-axis. So change theta to negative theta. Equals 1 plus 2 cosine negative theta. So it is symmetric about the polar axis. Because cosine's an even function, it doesn't matter. So yes, it's that one. The vertical line theta equals pi over 2. 2 cosine theta becomes r equals 1 plus 2 cosine pi minus theta. Which becomes 1, r equals 1 plus 2 cosine theta cosine pi cosine theta plus sine pi sine theta. Sine pi is 0. It's negative 1. R equals 1 plus 2 negative cosine theta makes it minus. So it fails. And how do we test the last one? We do that one as, and we can also change theta to theta plus pi. We have to, if it's across the origin, we have to check both of them. So 3 about the origin. So theta equals pi plus theta, r negative r. 2 cosine theta theta plus. So let's see if it comes back to this. Since it's plus, I put a minus sign there. Negative 1 cosine theta. This is 0. So r equals negative 1 plus 2 cosine theta. Nope. Because it didn't come back to what this equation was. 1 changed to negative 1. So it fails the origin test. If it's symmetric about the origin, then what you started off with is what you'll end up with. Well, what you'll end up with is both terms will be negative. You'll have a negative r equals a negative minus 2 cosine. So because if you drop it all out, then it's going to change. So we know we're only symmetric about the x-axis. It's a vertical shift. So plot some points. cosine. Right. So we're looking at whatever we got on the top, we'll just fold the page over, it'll be symmetric on the other side. So 1 plus 2 cosine 0, which is 1, so it's 3. 1 plus 2 cosine pi over 6. Pi over 6 is 1 plus 2 square root of 3 over 2. 1 plus square root of 3 plus 2. 1 plus 2 square root of 2 over 2. So it's 1 plus 2 1/2. So it's 2. Cosine pi over 2. 1 plus 0 is 1. So this is 0. Again, if you don't remember your trig identities or trig values, you have your cheat sheets with you. Cosine of 3 pi over 4 is negative square root of 2 over 2. So it's 1 minus square root of 2. 2 negative square root of 3 over 2. 1 minus square root of 3. And 1 plus 2 minus 2 is negative 1. Notice how these values here, because square root of 2 is bigger than 1. Square root of 3 is bigger than 1. And this is, so these three are going to be negative. So we're going to have a limicon with a loop in it. So at 0, it's 3. At pi over 6, that's 30 degrees. It's 1 plus 1.7, so it's 2.7. At 30 degrees. At 45 degrees, it's 1 plus 1. That's got to be a smooth curve. Pi over 3 is 2. Pi over 2 is 1. 2 pi over 3 is 0. 3 pi over 4, it's 1 minus, so it's going to be 1 minus 1, so it's negative. Pi over 4. 3 pi over 4. 1, 2, 3 pi over 4 should be negative. It's negative 1. It's negative 1. Yeah. But it's something like that. It's going all the way around. It loops back around. I would strongly suggest using a graphing tool. So yeah, the hardest part's gonna be these. Once you get those, plot them in there. Now we're gonna look at lemicons with loops. With inner loops, which we just did. R equals A plus B cosine theta. R equals A minus B cosine theta. R equals A plus B sine theta. R equals A minus B sine theta. With that condition. If B is greater than A, well, we should be easier if we did it this way. If they're both A and B are both positive and A is less than B, then we have inner loops. Now we're going to look at roses. Example 10. R equals 2 cosine 2 theta. Now we're dealing with double angles, which is what we're going to look at here. Now, the internal value will tell us the number of petals our roses are going to have. And as normal, we'll do the definitions later. So what do we have here? R equals 2, we should graph the equation. All right. So again, we have to check. First thing, always check for symmetry. The first one is the x-axis, which is the polar axis. we change theta for negative theta. R2 cosine 2 theta. I change it to R equals 2 cosine 2 negative theta. Again, cosine is an even function, so nothing changes. So it's symmetric about the x-axis. Then we do the line theta equals pi over 2, which is the y-axis. So we have r equals 2 cosine 2 theta equal, change it to r equals 2 cosine 2 pi minus theta. Which becomes r equals 2 cosine 2 pi minus 2 theta. Yeah, so we can use identity there. Theta, that goes to 0. That makes it positive 1. R equals 2 cosine 2 theta. Yes, so yes, it's symmetric with the y-axis this time. Because cosine of 2 pi is positive 1. And sine's 0. So it's 2. So we start off at ends. So it is symmetric with the y-axis as well. Since it's symmetric with the x-axis and the y-axis, it's symmetric with the origin. So that means we got to plot a whole bunch of points. So the third one about the origin. Yes, it's symmetric right there also. So let's plot some points. R equals 2 cosine 2 theta. 2 theta. We have it 0. Pi over 30. Pi over 4. Pi over 3. Pi over 2. Since it's symmetric about the x-axis and the y-axis, all we have to do is this one, then we have to flip it over and flip it over again. So 2 cosine 2 times 0. Cosine 0 is 2. Two cosine 2 pi over 6 is 2 cosine pi over 3 is 2 times pi over 3 is 1/2, so it's 1. Cosine 2 pi over 4, 2 cosine pi over 2. Cosine pi over 2 is 0. And 2 pi over 3. Two times pi over 3 is 1/2. Negative 1/2 is the second quadrant. Negative 1. 2 pi over 2. Negative 2. So at 0, it's 2. At 30 degrees, it's 1. At 45 degrees, it's 0. Pi over 3, it's negative 1. That's the same as that. So now if I flip it across the y-axis, flip it across the x-axis. It's supposed to be a 4-petal flower. My graph is too small. Yes. Ideally, because of our condition here, we'll end up with something that, since it's on the horizontal axis, something similar to that. It'd be wider, of course. But that's a rose. You could have 4 you can have 8. You is whatever your um, condition factor here is. That tells you how many petals you're going to have. For the rows, you have these functions: R equals A cosine n theta, and R equals A sine n theta. A is not equal to 0. It can be positive or negative. And n is either, it can't be positive or negative 1, because if it's a positive or negative 1, it's just a sine cosine function. It will tell you how many petals you'll have. And it can't be 0 either. Yeah, I should have gotten, what do you call it, Desmos out here. But yeah, these are the conditions for the rows. Definition of a rows function. Lemniscates. These are my favorite because that's what defines a propeller. Example 11. R squared equals 4 sine 2 theta. Again, we have to check whether it's symmetric about the x-axis, the y-axis, or the origin, or and the origin. Again, I love flying, so this is, I've always found love with this one because it's either going to be a single propeller or like have a double propeller. Oop. Or you can have multiple propellers inside there. So is it symmetric about the pole axis? Remember how we checked that? Theta to negative theta. What's going to happen here? Is a sine function odd or even? So this is going to change it to, so it's not symmetric about the x-axis. The line theta equals pi over 2, which is the y-axis. We do this by theta changing to pi minus theta. The sine comes into sine 2 pi cosine 2 theta minus cosine 2 pi sine 2 theta. Two pi is 0. 2 pi is 1. So 4. Negative cosine is 1. So no. Well, now let's check, is it symmetric at the origin? We don't know that. Because think about it. If we change r to negative r, isn't that going to fix it?
But if it's not symmetrical to X or Y,
What if it's graph like that? It could be symmetric here. It's not X or Y. So there are, yeah, typically if it's both, then it's going to be true. But if it is possibility that it could be neither vertical or horizontal, it would be diagonal. And what we're going to see there, it's going to be across the origin. So it change r to negative r, theta to pi plus theta. R squared equals 4 sine 2 theta. So change r to negative r. Theta plus pi. Negative r squared is r squared. So it's going to be sine 2 pi cosine 2 theta plus cosine 2 pi sine 2 theta. That's 0. That's 1. So it's sine 2 theta. So yes, across the origin. Now we got plot points. This is the part that I hate the most. So since we know it's symmetric at the origin, all we have to do is look at values in the first quadrant, and that's it. Well, sure, just find r and then square it. We have 0, pi over 6, pi over 4, pi over 3, pi over 2. Four sine of 0 is 0. 4 sine of 2 pi over 6, which is 4 sine pi over 3. Square root of 3 over 2. 3/4. 4 sine 2 pi over 4. 4 sine pi over 2. 4 times 1. Pi over 3. The sign will be positive. Nope. Square root of 2, so it's just 1/2. Square root of 3 over 2. Square root of 3 over 2. Yeah. What's the sine of 2 pi over 3? Oh, square 3 over 2. I square that. Square root of 3 is 3 over 2. Answers. Those zeros. That's our propeller. Well, since we only have these points, it's symmetrical at the origin. That's the other one. This section is not fun. Definitely use calculators. Ooh, the last one. Ooh. Example 12. We won't have time to finish it, but These are pretty cool. R equals, whenever you deal with e's, theta over 5. What was it? Snail shells. That's what that was a nickname of them. What they look like is when you graph these, they'll either be like this or like this. They're real cool functions. That's because we deal with a simple base, and the radical is the angle. Not not a XY value, not a integer, but it's a degree, which is even more cool. But talk about lots of work. I don't do that. Because you see that we have to go through all four. It's going to be symmetrical. It's not going to be symmetrical at the x-axis or the y or the origin, but we have to try points. And since it's not symmetrical by anything, we'll get points on each of these quadrants. So it's painful. All right, that does it for 9.2. What was 9.4 about? I would say we got more time. Oh, vectors. We won't have time for vectors. Did anybody take physics before? Okay. And basically, a vector